Hi, class. So we're continuing with our discussion of the Universal Law of Gravitation. We're going to cover just a little bit of the mathematics of it in this part of the lecture. So what I need you to be able to do is to compute a few numbers. If I tell you the properties of a planet, like its mass and its size, then you should be able to compute the strength of gravity. In order to do that, you need to know what the universal law of gravitation is. So if you're still feeling a little shaky with your math, make sure you go review the math videos that we put for the class at the start. I'll show you the universal law of gravitation here in the lecture. I'll talk about how we use it, and then in the actual notes that go with the lecture, if you look, I will compute by hand what the numbers I show you in the lecture actually are. Okay, so you can practice and do some of those yourself. Now, one of the problems we have when we talk about the universal law of gravitation is it is inherently a three-dimensional phenomena. And so as three-dimensional creatures, we certainly exist in 3 dimensions, 4 dimensions if you include time, but it's very hard for us to draw pictures so that we can talk to each other and try and get our ideas across. And so what you see here in the background is one attempt to kind of show that gravity has some structure. So you have a 3-dimensional object like a planet, but we've drawn the gravitational field, as it were. We're going to talk about these field diagrams here in just one of the planes, trying to draw it in all 3 dimensions and immersing this planet in some gigantic web of field lines would make this picture almost impossible to look at. Okay, so this is one of the hard things about gravity, is that conceptual visualization that we have to do, but we'll try and give you some tools here during this part of the lecture to work with. And if you and I talk like in office hours or over email sometimes, it's those kinds of diagrams that we'll fall back on to try and guide us in our thinking. Okay? Okay, so let me go ahead and start a few slides. So we said this during the first half of today's lecture, is that gravity is the only force that is important over the large scales of the cosmos. And the universal law of gravitation has been enormously successful for the entire 300 years since it was first written down, because we have seen that it works not only for describing life here on Earth, but it can get us to the moon, it can describe the orbits of planets in the solar system, it can describe the orbits of moons around planets, it can describe other binary stars we see, and indeed it can describe galaxies and all kinds of other phenomena that we see in the universe. So it has been enormously successful. And we use it for virtually everything that we do in astrophysics. So we're going to talk a little bit about that today. So the first thing I'm going to do is we're going to talk about this kind of visualization technique. This is a very robust conceptual way of thinking about gravity. It allows you to very quickly assess what's going on in any gravitational problem, and we fall back on it quite a bit. And you can use it to help with your own intuition when we are talking about things. I'll then show you the universal law of gravitation equation. Some of you may have seen this before if you've taken physics before, and then we'll apply it. We'll talk about surface gravity, and I will just mention here at the end Kepler's laws, which come from it. We'll come back to Kepler's laws when we talk about exoplanets in a little bit. So all the math, the beauty of the universal law is that all the math in the universal law can be represented with pictures. And being able to represent something with pictures is really quite valuable in terms of intuition, because it makes assessments much easier and much quicker for you. Okay, so you start with some mass, and so what I want you to do is remember those 4 tenets that we said about the universal law during the first half of today's lecture. We said that it's an attractive force. We said that it depends on the size of the mass, how much mass there is, and it depends on how far away from the mass you are. Okay, so what I want to do is I want to represent the gravitational force of this planet that I've put here in the middle of the screen with a picture. And so the way I'm going to do that is I'm going to pick some distance away from the planet, represented by the red circle, okay? And I'm going to draw an arrow that represents the gravitational force that planet's exerting on me if I stand at any of the places there where I put an arrow down. okay? So that red circle is all the same distance away. So the gravity anywhere on that red circle is exactly the same strength. So all my arrows are exactly the same length, but the force is always pointed towards the planet. So the arrows all change direction, okay? Now, those of you who remember your previous training, if you've had physics before, will recognize these arrows are what we call vectors. They have a magnitude, a length, and a direction, okay? Now, if I draw another circle closer to the planet, the universal law of gravitation says that the force must be stronger because I'm closer to the planet. Gravity depends on the distance. So I draw a very similar diagram to the first one I drew with the outer circle. And the inner circle, I'm going to draw an arrow. They're all the same length, but since I'm closer and the gravity is stronger, I'm going to draw the arrows longer to indicate that the gravity is stronger. Okay, now I could do that for any number of red circles that I want on this diagram. And if I did that, what you would notice is that all the arrows I draw basically point in the same direction. Okay, and they all overlap with each other if I draw enough circles. So what I'm going to do is I'm going to not draw the arrows at all. I'm just going to draw these lines that start at the planet and go all the way out to infinity. Okay, basically where I would have drawn the arrows. Okay. This diagram, what you're looking at right now, is what's called a gravitational field diagram, okay? Now, I told you that this could replace our mathematical expression for the universal law. So how are the things that we know the universal law says encoded in this diagram? Okay, so the strength depends on the size of the masses, and it depends on the separation of objects from the mass creating the gravity. Okay, well, the size of the mass is, if you have a larger mass, you just draw more field lines. Okay, so over here on the left is our original planet. It has 8 field lines around it. Over here on the right is a much bigger planet. It has 16 field lines. And if I had an even more massive planet, I would draw more field lines. If I had a smaller planet, I would draw fewer field lines. So the number of field lines that I draw is related to the size of the mass that I'm talking about. Okay? Now, what about the strength? Well, the strength has to depend on the mass, and the strength also has to depend on the distance. So the way we write down or the way we indicate the strength of gravity is you ask, where are you sitting in this diagram? If you're a person flying around this planet or a life form living on the surface of the planet or what have you, and you basically count how many field lines are near to you. So this is something we call the density of the field lines. So how does that work? Well, let's imagine someone. So here's Stick-Spock, okay? So Stick-Spock's in orbit around our original green planet. And if I draw a little circle around Stick-Spock, his spaceship basically, right? And I look at how many field lines are inside his circle, I get 2. Okay, so that's some measure of the strength of gravity. Now let's imagine Stick Geordie over here, the exact same distance away from this much bigger planet. If you draw the same circle around Stick Geordie, you see there are more lines that go into his circle. So what that means is, compared to Stick-Spock over there around the small planet, Geordie's near a much more massive planet. Gravity is stronger for more massive planets, and indeed, the field diagram shows Geordie sees more more gravity than Spock sees the same distance away from their planet. This is one of the ways that Geordie can measure the mass of the planet, is he can just measure how strong the gravity is at a known distance away. But the strength of gravity also has to decrease with distance. So does that work? Well, sure it works. So if I draw Stick Picard now around the big planet, he is farther away from the big planet than Stick Geordie is. Okay, but you see he finds himself in a situation not unlike Stick-Spock. He's farther away from the big planet, so the gravity's gotten weaker, and indeed there are fewer lines going through his little circle. Okay, and so there is a place at a certain distance from the big planet where the gravity is exactly the same strength as he might experience being close to the small planet. Okay, so everything about the universal law that we said it had to have is contained, can be represented in these field diagrams. And so very often I will never do a calculation at all. I'll draw these field diagrams and kind of work things out in my head and do it this way. You can also check that your calculations are correct by drawing the field diagrams and seeing if things make sense to you. Okay, so these are a tool for you to use to help with your intuition. You won't have to necessarily do any work with them, but they're a good thing to become very conversant in to kind of help you along. But we are going to have to calculate some numbers. So in order to calculate some numbers, we do have to write down the actual mathematical law of the universal law of gravitation. So that's what I'm going to do here. Okay, so it depends on the masses of the objects that you care about. So here it might be, say, the sun and a planet, but in the previous examples, it could be a planet and a person. It could be a planet and its moon. It could be a moon and a life form living on the surface. It could be any two masses. All masses attract each other. That was one of the things we learned in the first half of the lecture. What matters here is the separation between them, and I've drawn this as the separation between the masses. Technically, it should be the separation between the center of the two masses, but it just made the diagram a little bit cleaner if I did it this way. Okay, so if I use these values, big M for one mass, little m for the other mass, and R for the separation between the two masses, then the universal law of gravitation can be written in the following way. It's a fraction, okay, and it is this number g times the mass of the big planet, represented in kilograms, times the mass of the other mass, represented in kilograms, divided by the distance squared in meters, okay? So the question is, what is that big G? Well, that big G is, as we call it, a fundamental constant of nature. It's something that's built into the structure and fabric of the universe. It's a number. It's the same for everyone. It's a constant about the way the universe is put together. Okay, it's called Newton's constant because Newton was the first one to write it down, and it has the value that I've written there, 6.67 times 10 to the minus 11 meters cubed per kilogram per second squared. Okay, so if I ever want to compute the gravitational force between the moon and the Earth, I take that value of G, I multiply it by the mass of the Earth, I multiply it by the mass of the moon, I divide it by the separation between the Earth and the moon squared, and you will get the gravitational force between the Earth and the moon. Okay? Now, this is what you will hear physicists call an inverse square law. That's because of that 1 over r squared. Okay, and that is important in many situations. We will encounter other 1 over r squared laws, inverse square laws in this class, in particular when we start talking about light. But just be aware that you'll hear that terminology sometimes. Okay, so let's put this to practical use. Why are we even talking about this? So we're talking about this, eventually we're going to have to talk about exoplanets, and we're going to need this to talk about orbits. But today I introduced it because I want to talk about how strong is the gravity that you feel if you're standing on the surface of a planet. Okay, and I want to talk about whether you're standing on the surface of the Earth, standing on the surface of the Moon, standing on Mercury, standing on Mars, Europa, Enceladus, wherever you are. Okay, and the way to calculate that is with the universal law of gravitation. Okay, so let's do it for the Earth, and then we'll do it for the Moon so you can see how it goes. Okay, so let's imagine me, that's the Lego version of me, standing on the surface of the Earth. Okay, so the Earth is the big mass M, I'm the little mass m, and I'm standing basically the radius of the Earth away from the center of the Earth. Okay, this is a little bit more than that to go up to the center of me, but my height is very short to start with, but it's very small compared to the size of the Earth. So we're just going to take this to be the radius of the Earth. Okay, the strength of gravity that I feel, the strength of gravity you feel right now, sitting there watching this lecture, is what we call 1G. Okay, now sometimes that's abbreviated 1 with the letter G. Don't ever do that because it looks like you're writing 1 gram. Okay, so if you write 1G, write GEE or G Earth so that we know what you're saying. If you write 1G as in G, then it looks like you're writing grams and it's very confusing. So don't do that, okay? So the strength of gravity you feel is called 1G. So how do I calculate it? Well, I use the universal law of gravitation. Okay, so I wrote out the universal law of gravitation there, and all I've done is I've factored it in a very clever way. It's not clever, I just factored it, okay? I pulled that little mass m out, because that's the mass of me, and I left all the rest of it together in the parentheses there. And you'll notice that everything in the parentheses there is about the Earth, okay? So that quantity in parentheses is what we call the surface gravity of the Earth. And sometimes we'll label it G sub S, okay, for surface gravity, okay? So if I take and I put in the value for G, 6.67 times 10 to the minus 11, I multiply it by the mass of the Earth, 5.97 times 10 to the 24 kilograms, and I divide it by the radius of the Earth squared, 6.3 times 10 to the 6 meters squared, then I will get the surface gravity of the Earth. And the surface gravity of the Earth is a number that comes out to be 9.80 meters per second squared. Now, some of you will recognize that. If you've had physics before, you were taught that that number is called the acceleration due to gravity. It is the acceleration due to gravity on the Earth, not on every world. So this is actually what we call the surface gravity of the Earth, okay? You'll notice I didn't need to know the mass of me. The mass of me doesn't matter. The Earth's surface gravity is what the surface gravity is, whether I'm in the problem or not. You could put the mass of me there. You could put the mass of your cat there. You could put the mass of a tardigrade there. You put whatever you want there for the mass, okay? It doesn't affect what the surface gravity of the Earth is. Surface gravity of the Earth only depends on the Earth. And it tells me what I, as something on the surface of the Earth, am experiencing, okay? So let's do the same thing for the moon, okay? So suppose I'm a tardigrade living on the surface of the moon, okay? What gravity do I feel? It's the exact same problem as the one I just showed you for the Earth, okay? So let's do it. So I write out the universal law of gravitation. The surface gravity is that term that's right there in parentheses. And I'm talking about the moon now instead of the Earth. So the thing that goes in there are all the values for the moon. G, the universal law of gravitation's constant, Newton's constant. M, the mass of the moon, you can go on Wikipedia and look it up. R, the radius of the moon, you can go on Wikipedia and look it up. You put them all together, and if you compute the surface gravity of the moon, you get that it is 1.62 meters per second per second. If you divide that by the Earth's value, 9.8, then what you'll find is that 1.62 over 9.8 is about 1/6, which is where NASA gets that number that you always hear them say, which is the gravity on the surface of the moon is about 1/6 as strong as the gravity here on Earth, okay? Now this is important for us because the gravity of a world tells you a lot about the environment that an organism is going to experience. How strong is the gravity that it has to resist and operate under? It is the gravity of a world that will tell you about the conditions on that world. For instance, if the surface gravity is too low, the world can't hold on to its atmosphere. If the surface gravity is really strong, maybe it has collected a lot of material and it's not at all like the surface of our Earth at all. Jupiter is a good example of that. Okay, so the surface gravity ends up being important to us for a variety of reasons. So being able to calculate this number is something you should be able to do, and we'll come back to it repeatedly when we start talking about other worlds, particularly here in the solar system. Okay? Okay, the last thing I want to mention, as long as we're talking about the universal law, is that it's connected to something called Kepler's laws of planetary motion. We will talk about them formally when we talk about exoplanets, but let me just mention them here so that they're circling around in your brain before we get there. So there are 3 laws of planetary motion. They're called Kepler 1, Kepler 2, and Kepler 3. So the first law says planets travel on ellipses with the sun at one focus. Okay, so Kepler lived about 80 or 90 years before Newton did. So this was before the publication of the Universal Law of Gravitation. So we didn't know anything about orbits, but Kepler had worked out everything about the orbits of the planets from observations of the planets. And at that time, everyone thought the planets moved on perfect circles, but Kepler discovered they don't. He discovered that they move on ellipses, which are basically flattened circles, and that the sun sits at what's called the focus of the ellipse. Okay, so that's his first law of planetary motion. The second law is that planets sweep out equal areas in equal times. Now that sounds like a weird statement to make, but it makes sense in the context of the picture that I've drawn there. So imagine the planet, Jupiter there, is going around the sun, okay? And if I point to where a planet starts, and then I set my stopwatch, and then I let the planet move along its orbit for some amount of time, and then I stop my stopwatch, it will sweep out some area that's basically the shaded in green part there. So I've basically shaded in all the area between Jupiter and the sun as it traveled along its orbit for some certain amount of time, okay? So if you imagine we start and do that for the part on the right side of the orbit there. Then we wait a little while and Jupiter gets to the other side of its orbit and we do the same experiment. And so I mark Jupiter's starting point, I let it move for the same amount of time, it sweeps out a little bit of its orbit, and then I stop. And so it makes that second green wedge. What's the same between the green wedge on the right and the green wedge on the left is the amount of time it takes Jupiter to go between the two spots indicated. But what Kepler discovered is that the area of those green wedges is exactly the same. Okay, and that was a great, great observation. It describes something that was not really understood before that time, which was basically planets move faster when they're close to the sun, and they move slower when they're farther away from the sun. And this put a very strong quantitative way of making that statement, because they didn't have the universal law. They couldn't prove that at that time, okay? The third law is probably the one we use the most often. It's usually called the harmonic law. It basically said that the time it takes a planet to go around its orbit is related to the size of the orbit. And written in the language of ellipses there and orbits, it says the orbital period, the square of the orbital period, the time it takes to go around its orbit, is related to the cube, the third power, of the semi-major axis, which is basically half the long axis of that squished circle. For a circular orbit, this would say that the square of a planet's orbital period is related to the cube of the radius of the circle. Okay, so the semi-major axis of an ellipse is just the radius when you're talking about a circle. Okay, so we'll come back to all of those. We will use them repeatedly when we talk about exoplanets. We'll mention them when we talk about some of the moons of Jupiter and Saturn here over the next week. But I want you to be familiar with them so that when I say we use Kepler's third law to find the orbital period, you're not completely drifting on the ocean. Now, the last thing I will say about these is these are traditionally called Kepler's laws of planetary motion because he discovered them for the solar system. We tend to today call them Kepler's laws of orbital motion or simply Kepler's laws because they apply for all orbits, not just planetary orbits. You'll see the way we've written them here. They're written, for instance, in terms of the sun. Okay, that's the way Kepler expressed them. But when we start talking about planets orbiting other stars, that's really not going to work so well, right? So, so these are very generalizable to all orbits, and we'll talk about that when we come to it. Okay, so that is all I'm going to say for this bit of the lecture. I hope you're comfortable with this. If you're not, do a little bit of work with your calculator. And if you have questions, certainly stop by and ask me. We'll come back to these concepts repeatedly, and we will use them repeatedly over the next few weeks. Okay, so I hope you're all doing well. I'll talk to you soon.